Hello. We've seen that things can either be classed as luminous or non-luminous. A luminous object is something that gives off its own light. For example, there's a ray box and it has a light source. Other things don't produce their own light, like a bit of paper. And we can see that because of the light that comes in the window and reflects off that. We can only see something that is non-luminous if there is a light source that shines light on it. And that light reflects off it and goes into our eyes. But there are different types of reflective surface. This is not what we normally think of as reflective. We can see it, but we can't see an image in it. Something that we normally think of as reflective is a mirror. The main difference between a bit of paper and a mirror is that paper, or skin, or clothes, or wood, has a microscopic texture. So whenever light hits it, it scatters in all directions, which means somebody over here can see it, and over here can see it. A mirror, however, is very, very smooth, which means any light hitting it will reflect off in a very predictable way, which is why we can see a very precise image. The light isn't scattered. And what we're going to do today is consider how does light reflect off a mirror, and it's called a plane mirror. Plane mirror is a flat mirror, so we're not concerned with curved mirrors, just flat mirrors. And so there are a few things that we have to consider about this. What's a mirror made of? A mirror is made of glass, but it's not the glass that's reflective. On the back of the mirror, there's a reflective metal layer. It used to be silver, now it's usually aluminium, sort of sprayed onto it, and then a bit of paint or plastic coated over the back. The glass at the front is to protect the reflective surface inside the mirror. So that's important to remember. Light reflects off the back of the mirror, not off the front of the mirror. Whenever we draw a diagram of a mirror, it looks like this. And this top side is the reflective side, and the side with the hashes along the back is our non-reflective side. Whenever we do experiments like this, we get a mirror, but we hold it like this, and we can use, well, in school we use like a wooden block with a slot in it, a bit of blue tack, to hold it in place. Now I'm lining this mirror up so that the back of the mirror just covers my pencil line. Now you can see the back of the mirror is on the pencil line. If I use a ray box is just a bulb, a light source with a slit in the front, which allows a very narrow beam of light to come out. You should be able to see the light coming in, hitting the mirror, and reflecting off. What we're going to do is we're going to plot different rays coming in and the rays coming out and see what relationship there is between the angle between those in the mirror and see if there's a pattern. A few bits of terminology. A ray that comes in is called an incident ray, and the ray that comes out is called a reflected ray. I mentioned some angles. We never, ever in physics measure the angle between the ray and the mirror. We don't measure that. The reason for that is if we do have a curved mirror, it's impossible to measure to a curved surface accurately. So we need to draw another line. And this line is a line that comes out of the mirror at 90 degrees from where the ray hits the mirror. And this is called a normal. And in fact, we draw that before we do any more experiment. I'll show you that now. You have to use a protractor for doing this. Put a mark at the point we're going to aim. Line up my protractor with the center of the mark. Another mark at 90 degrees. We join that with a ruler. And that's our normal. So I'm going to put 5 rays of light, shine them in at this point with the mirror in place, and I'm going to mark the position of the 5 reflected rays. And we're going to measure the angle between the incident rays and the normal, and the angle between the reflected ray and the normal. And we're going to compare them and see what happens. I'm going to draw in 5 rays first, the incident rays first, so I can line up my ray box, and that makes things a bit easier. My first ray, I want to come straight down the normal. So I put my mark there. And then I'll go in 15-degree increments anti-clockwise. So 15, 30, 45, and 60 degrees. And I'll draw in those rays. And we want to be as precise as possible when we're doing that. I'm going to put arrows on to show the direction of the ray. And those are the incident rays. And I'm going to label them. So that's I1, I2, I3, I4, and I5. And always remember, we measure the angles between the ray and the normal. We're going to put a results table on our page to record the angles of incidence, these angles, and our angles of reflection as the rays come out. So we'll put in a result table now. And our angles of incidence, our first one was 0 degrees because it's coming right in along the normal. Our second one was 15 degrees away. I3 was 30 degrees. I4, 45 degrees. And I5 was 60 degrees. One very common mistake is people measuring this angle, the angle between 2 rays. We don't care about that angle, it's only the angle between the ray and the normal. The way that we plot the position of the reflected ray is by using small x's. So let me show you this. Get my mirror, and I'm going to line my mirror up so the back of the mirror covers the line. Hopefully you can see that now. It's very important that when you do this that we don't nudge the mirror throughout the rest of the experiment. We line up the incident ray with our line. And it's maybe a bit faint, but you should be able to see our reflected ray coming out this way. I'm going to put 2 X's on the page. One down there, close to the mirror, and one further away. In fact, I'm going to close the curtains to make this easier to see. And I want my X's to be right in the middle of the line. And I'll repeat that for each of my 5 rays. And our final ray is travelling along the normal, so it has an angle of incidence of 0 degrees. And we can't really see the reflected ray, and that's because the reflected ray is coming straight back along it. Which means it too should have an angle of reflection of 0 degrees. I'm going to pause here and scan this page. If you have a printer, you can print this out, and I'd like you to complete the lines yourself. So you're going to draw in the lines joining the X's, and they should, if you've done it correctly, meet up at this point. Then we're going to measure the angles between each ray and the normal. If you don't have a printer at home, contact me in Google Classroom and I will send you out a completed version of this. But now I'm going to scan this. Okay, now I've scanned that. And so if you have a printer at home, you could print that out and do what I'm going to do now. I'm going to complete my reflected rays. And don't forget, we did have a ray coming straight back. And so that will be R1, R2, R3, R4, and R5, where these are the reflected rays. So these angles, we normally just give the letter I to. These angles, we give the letter R to. I is the angle of incidence. R is the angle of reflection. Now we need to measure these angles, not forgetting to measure from the normal out to the ray. Now, I'm not going to show you these numbers. I'll hide them now. But if you don't have a printer, let me know and I will send you this completed page with the numbers so that you can interpret the results yourself. Line up your protractor with the 0 along this line, the normal. And then we can just simply read off the other way to see what the angles are going to be. Now what I can see from my results is that I've maybe nudged my mirror a little bit and not perfectly lined up, but hopefully, whenever you look at this, you should see a fairly good relationship between these two columns. And let's see what you think about that.